Hello everyone, today we're going to be looking at the testing of a radio, a HF radio, a commercial radio, which is a Vertex VX 1400 HF 0 to 30 MHz SSB radio. One of the unique things that challenge radio engineers these days when they're dealing with HF's radio equipment is the ability to be able to test it on radio test instruments such as we have here. Most radio test sets don't accommodate SSB modes for transmit anyway. They do allow you to use AM obviously, and you can use AM to test SSB radios, but today I just wanted to show you three test sets of how they're used to test such an SSB radio and what capabilities and functions that they present the radio engineer who wishes to make these tests specifically for upper sideband, lower sideband and what have you. But this radio is quite a powerful one. It's a commercial radio, it's not an amateur radio set. It's got fans at the back as well to keep it cool. It works off of 12 volts DC, and basically it's set up with memory channels at the moment, but you do have a VFO mode on it, so you can put any frequency you want in it. Now the thing with this radio is it's mainly used in countries such as Australia, South America, Africa, places where there are large expanses of land without good mobile phone or satellite phone coverage. Indeed, Antarctic surveys and some of these really difficult areas of the world that are almost uncontactable with satellite or landline or even cellular communications. Indeed, people that buy sat phones to make calls in remote parts of the world often get problems when they're in mountainous terrain or in valleys where the constellation of satellites block or are blocked by the surrounding terrain. And quite often some of these expeditions that go on, they do have to buy or rent quite a few different satellite phones and operate on different satellite constellations in the hope that they can get a good signal when they need it. But the thing is, with HF radio, obviously these are used more widely. Anything from distance learning for pupils in Australia, I've dealt with things like that before, on board ships that are crossing the Atlantic and the Pacific Oceans, for marine radio and distress calling. And again, these radios don't tend to suffer with problems from atmospherics that can present to the satellite phone. And in addition to that as well, they're used to keep contact with remote outposts and communities that are otherwise living in very remote locations and hence can't make reliable communication to the outside world to raise medical help, get food supplies, and also to just basically have a chat with people and keep in touch with family, you know, from across the world. Obviously the ranges that we can get from HF SSB radio are immense. I mean, we can get round the world coverage on this radio alone, so it's a very good survivalist tool if you're ever out in the outback of Australia and you find yourself in difficulty. You'll find a lot of people that live in that area will have these radios installed in the vehicles, and they are a lifeline. Indeed, in countries like Australia, they operate a system where you can pay a subscription, and there are set frequencies which you can use, and this is the same as well around the world, where you can use a cell call tone which is programmable in the radio, and it will give you a connection then to a base station, HF base station in that country, which will allow an outside phone call to be made, a telephone patch phone call to the radio, and you'll be billed later on for that call. So you can not only raise emergency assistance and help, as we can see here, we've got an ITU channel in, an international telecommunications union channeling, but you can also use it to receive phone calls coming in as well as make phone calls going out. Although it's not full duplex, you know, it's simplex. You have to unkey to hear the other person talk back, and you obviously, when you transmit, they can't talk over you on the phone because obviously you're not able to hear what they're saying while you're broadcasting. But it allows radio communications over long distance to raise help or contact family, etc., either directly or indirectly through various means. And so in countries like South America, for example, and other major continents like that, where landline and cellular communications is quite sparse, particularly in rural areas, these radios are very, very important as well. And obviously they're very useful as well on board ships that sail across the big seas, to keep communication there for problems, and to raise help where needed on the marine HF international distress frequencies. So there's so many applications for these radios, it's unbelievable. Now this particular radio does 10 watts, 50 watts and 100 watts output power, and as I said, one of the unique challenges is testing these radios. Now the Marconi 2955, for example, doesn't do SSB. It does FM, AM and phase modulation. So we can use AM to test the receiver. It's more of a general test of the receiver though. And the transmit side, we can transmit on the SSB radio into the Marconi, and we can obviously measure TX power. We can't really demodulate the SSB audio, or what I'm saying, into the microphone very well, because obviously it's an AM radio test set when it's set as an AM mode. Likewise in FM we wouldn't be able to hear it either, but we can measure the TX power on there. So the Marconi is quite limited for SSB testing, but it has partial capability. Here we've got the Roden-Schwartz CMS 54 radio communications test set. This test set has SSB modes enabled on the software options, so that you can select RX SSB testing and obviously TX SSB testing. It does have a weird menu system though, I must admit, but on this test set we've got the usual radio test that we can do on FM and AM as well as SSB with this SSB option. So we can just select SSB, and then we've got the capability to look at LSB modes, lower sideband, upper sideband and CW modes. And same for RX testing as well. We can also generate a lower sideband, upper sideband and a CW signal if we want to do. CW tends to be used for Morse keying, for sending Morse code. It's also used in other digital applications such as radio teletype, and keying in general for variety of different communication methods is CW. Lower sideband and upper sideband is just where, if you don't know about sidebands, unlike FM and AM where we have a carrier wave, and in the case of FM we have, if we have a 30 watt transmitter for example, we are transmitting at 30 watts when we key the microphone. Now if we're speaking to the microphone on FM, obviously the carrier wave frequency modulates left and right of the centre frequency. In other words, the centre carrier wave will modulate, deviate left and right in proportion to the speech that we give into the microphone, and that's called FM deviation. And we can change the deviation depending on how loud we're speaking to the mic, but in 12.5 kHz radio systems for example, the deviation would peak at plus or minus 2.5 kHz, and on 25 kHz channel spacing it would deviate at plus or minus 4.5 kHz, etc. Depending on the radio system, the channel spacing, we'll set the deviation in the transmitter appropriately on FM. However, the carrier wave and the RF energy remains the same at 30 watts if you're a 30 watt transmitter. If it's a 10 watt transmitter, it'll be 10 watts. So it doesn't matter if you speak into the mic or not, there'll always be 10 watts RF power leaving the radio to the antenna and being radiated, broadcast off from the aerial. With amplitude modulation, or AM, the carrier wave is again produced on the frequency that we wish to transmit on. However, only a proportion of the total output power is transmitted when there is no speech. So if we don't speak into the microphone and we just key the mic up, there'll be about 20 to 30% of the RF power. So for example, as a 30 watt transmitter, for example, if you keyed up the transmitter without speaking into the microphone on an AM radio, there might be somewhere between 10 to 15 watts of RF coming out. But when you modulate into the microphone, you start to speak into it, then the carrier will be amplitude modulated, where the output power of the RF amplifier will be modulated so that it would peak at, say, 100% modulation, for example, which would equal 30 watts if you're using a 30 watt transmitter. So depending on the level of speech that you put in, and all those factors will depend on how much modulation depth there is, and that's what we call peak envelope power. So, you know, if we're broadcasting an AM signal and we are shouting into the microphone at very loud levels, then there will be more peak envelope power produced, more RF output power in synergy with the speech than there would be if we would speak very quietly into the microphone. And so AM is amplitude modulation. We're modulating the amplitude of a carrier. Now in sidebands, we're using a similar thing to AM, except what we're doing is we are creating a suppressed carrier. So instead of having a carrier wave when we transmit, we don't have a carrier wave. We only get an RF energy produced when we speak into the microphone, because the carrier is what's called suppressed carrier. So we have left and right sidebands on any signal, be it whether it's, you know, FM, AM or whatever modes you're using. There are always sidebands there, although we in general terms don't use the sidebands very much. But in sideband communication, or SSB communications, we take advantage of those upper and lower sidebands, and we can use them for communication channels of their own. And so in upper sideband mode, for example, we suppress the carrier and we have a slight frequency offset above the carrier, which would normally be the frequency we'd be talking on, and that is the upper sideband. Likewise, the lower sideband will be an offset slightly below what would be the carrier frequency, and that produces what's called a lower sideband. So we can switch between upper and lower sideband, and we can use them individually. And then of course we've got carrier wave, where we can use that for sending Morse code, or CW. So those are the different modes. Now likewise, when we're generating a signal to the receiver, we need to broadcast whether it's a lower sideband or an upper sideband if we want to do accurate testing. If we don't want to do accurate testing of the sidebands themselves, for example, there might be an issue with a radio that's reported where the sidebands are not working properly on receive, but they are on transmit. If that's not the case, we can just do a general test, which would represent both upper and lower sideband, just by sending an AM signal out from the test set, and that is suffice for using it for testing the receiver in the radio, because we're generating a frequency that's amplitude modulated, which sidebands are amplitude modulated as well, except we're just suppressing the carrier. So insofar as testing receive is concerned, we can generate a receive signal. We're using amplitude modulation. The radio will pick that up, and we can listen to the 1 kHz test tone or whatever test sensitivity of the receiver. However, it's always nice to be able to do proper accurate upper sideband, lower sideband testing when you're setting up the frequency accuracy of a USB and an LSB radio. There are other modes in the sidebands availability, such as DSB, double sideband, but in most communication systems use LSB or USB, upper sideband, lower sideband. And so the Marconi 2955 is limited for SSB testing. However, the Roden Schwartz CMS 54 has got the SSB capability on it. So here we're going to generate a signal on upper sideband, and I think, I'm not mistaken, 8.297 RF level. I think we've got a test. Oh, that does help, doesn't it, when you plug in the RF port on the radio test set. So here we are, schoolboy error, not plugging in the RF lead. So that would be CW mode. LSB, obviously we're not on LSB on the radio, we're on upper sideband, so obviously we wouldn't expect an LSB signal to be received. And then we've got upper sideband as well. So, and we can test the receiver sensitivity in microvolts, how sensitive a squelch is, and do all kinds of testing. Okay, and then likewise on transmit mode, and we can just turn that down so we can key up. Now at the moment, the thing is with this radio test set is it's quite a complex beast to set up, because you've got to adjust all kinds of parameters and settings, and it's not particularly user friendly format in comparison to, say, the Hewlett-Packard or the Marconi. But you can get the gist of it once you've had a little play for a while or read the manual. But if we broadcast on this radio set to, I think it's 50 watts there, so if I transmit on that, 1 2 3 4 5 1 2 1 2 5. So again, you've got different modes settable on this for capturing the RF power. And there's another little hidden menu, which is a pain in the backside, that you have to remember to get to. So you can select peak envelope power. You can hold the power as well. Power hold. So when you transmit, you can measure the peak power. 5 1 2 3 4 5. So there you can see we've got a peak envelope power on that particular modulation test of 27.67 watts. The trouble is that with this test set, it's a little bit sort of clunky. You can hear all the relays clicking away inside. It's trying to measure the power and, you know, and get through that side of it. So yeah, the test set's good, but very clunky in comparison to the Hewlett-Packard radio test set, which I'll show you now. So on the HP Agilent HP8920V, we have an SSB mode on here, although it's not upper sideband and lower sideband like you can test on the Roden Schwartz. It does have still a good capability. So likewise, on receive, for example, first, we set up the frequency already on receive. If I turn this up now, that's the radio receiving on that frequency, and we're on 8.297 megahertz. What we're doing is we're modulating it, and we've got, I think it's 30% modulation, so we can increase that. It's 50, 60%, 80, 90, and that'll be 100% modulation of the carrier. So if we set it at, say, 60% modulation, and then that should do it, I think. I can't find the percent key, which is somewhere knocking about here. Oh, there we are. Yeah, is that not it then? That's another thing about the Hewlett-Packard. Ah, there we are. Look, it's percent's there, just written above it. There's also a percent written there as well, but anyway, that wasn't the right key. and then we can test the receiver sensitivity. That's 1 microvolt. So we're using AM there to test the receiver. Now it's not a USB and an LSB test, but it does show the performance of the receiver. So on transmit, for example, when we look at the radio AF in, analyzer in, you can select FM mod, AM mod, obviously SSBD mod as well, so we'll select SSBD mod. So now when I transmit, we should be able to hear what we're saying on the test set. 1 2 3 4 5 1 2 1 2 5 4 3 2 1 1 2 1 2 3 4 5. So you could see as well the RF power is quite responsive. It's set at 50 watts, so we're getting nearly 60 watts RF power. And then we've got a 100 watt mode as well, so that's a 100 watt mode. 1 2 3 4 5 5 4 3 2 1 1 2 1 2. So as you can see, you can do those measurements on the HP Agilent as well. Now the problem is with, like most radio test sets, they're made for a particular market. The Roden Schwartz is in particular set up to do SSB testing as well as all the other variants of testing. So is the 8920, and it's quite responsive. A lot easier to use is the 8920 than the Roden Schwartz. And then of course the Marconi 2955 has got some test capability for SSB, but again, I think the Roden Schwartz is a little bit clunky for the transmit side, measuring the TX power. The relays are chattering all the time and trying to make a measurement based on what's coming in at that precise picosecond, whereas the Agilent's very quick and very responsive. Sometimes you have to use a separate bird power meters and things to test SSB radios, because test sets are not designed to respond that quickly to changes in the transmit power, and it's very difficult for them to try and tune as well as measure the RF carrier at the same time, and there's a lot of setup needed in the test set sometimes to just get it to be stable with what you're measuring. Which is fine if you know what you're measuring is okay, but if you're repairing a fault in a radio, you really don't want to be messing around for too long on the radio test set, unsure as if it's the test set that's not set up properly or the radio that's still got a fault on it. Whereas at least with the HP, you can generally see there with how quick and responsive it was that it would measure SSB quite accurately and keenly, and so it will give you that level of confidence that perhaps the other two don't offer. But certainly this is a digital version of the Bird 43 power meter. This is a Bird 5000, basically 0 to a gigahertz, up to 500 watts capability of RF power measurement. And a lot of people do still prefer to use the separate analog or digital RF power meters, and rather than use the test sets, because the test sets generally have got around about 50 to 75 watts RF input, and so SSB radios, as you've seen there, can produce well over 100 watts quite easily, and they can obviously damage the test sets for prolonged periods. I think the Roden Schwartz is set up more so that you transmit into the microphone audio path a 1 kHz test tone, so that it gives the test set a chance to lock on frequency and thus be able to measure the power accurately, whereas excuse me, just shouting into the microphone doesn't allow it to test the power that accurately. But it did measure the power, don't get me wrong, but it's sort of hit and miss really. So there you are, that's a little rundown on SSB testing on 3 different kinds of test sets. Thank you very much for watching the video.